Okay, so tonight the chapter 10 and 11 stuff. This is, remember, not on the last test. It's not on the Proctor test. It's only 6 through 9. So this will just cover. This will only have a homework and quiz to it, not on the Proctor test. Okay, so let me move this around here. Okay, so let's talk about 10.1 here. This is talking about linear correlation or correlation. So the definition I have there exists. Linear correlation exists between two variables when there is correlation in the plotted points of paired data results in a pattern that can be approximated by a straight line. Okay, so let me kind of explain what that means. I'm going to scroll down here for a second, and we have these graphs, and what we're measuring is how related the two variables are. So in this graph A, these dots are an exact straight line. And since they're an exact straight line, that has perfect it's perfect correlation, but it's in the negative direction because as one goes up, the other variable goes down. Okay. Where B, you still have that same general, downward pattern, but it's not in a straight line. Okay. Where C, there seems to be no pattern at all. Okay, so kind of keep that in mind. And what these properties of linear correlation are is it has to be between -1 and +1. Okay, so we saw the case where -1, where you have a graph and that's a straight line negative direction. Okay, if you have a positive correlation, +1 correlation, it'd be the same thing, but in the points would be in a straight line, but in the positive direction. Okay. So what we're going to do is we're going to measure that relationship. Let's see. Yes, Caleb, I will. I forgot to do that. I forgot to post in chapter 9. So yes, I'll do that after class. And way that we measure that is with this big calculation here, this pretty big formula. We're going to have StatCrunch do that for us. None of these individual calculations are very hard, but when you combine them all, it's very, very tedious. So I'm going to go down those graphs, and I'll come back to this in a second. So, we saw this graph A has a perfect negative correlation. An R value of -0.94 is pretty close to straight line. This last one at R of plus 0.08, this looks like no correlation at all. And then we have, positive correlation, whereas one variable goes up, so does the other. This is a perfect straight line. So that'd be +1. Here you have positive because as one variable up is going up, the other is as well. But they're not in a straight line, but there is a pattern to it. So that's pretty close to 1. So basically what happens is the closer it is to 0, like this graph C, the less correlated it is. The closer to positive or -1, the more correlation there is. Okay, so let me say that again. The closer to 0 it is, the less correlation. The closer to positive or -1, the more correlation. Okay. So our hypothesis here is we have HO. This is a new Greek letter. This letter is rho. So our HO, our null hypothesis, is rho is equal to 0. That's just our population correlation is equal to 0, meaning there's no linear correlation. So we assume no linear correlation unless we can prove otherwise. So we assume there's no correlation. If we can find an R value that's close enough to positive or -1, that means there is linear correlation. Okay, so we reject HO and show that there is linear correlation. All right, so let's look at an example of this and kind of put all this together. We have this critical value table. We'll come back to that in 1 second when it makes sense. All right, so what we have here is it says, listed below are the overhead widths of seals measured from photographs and the weights of seals. The purpose of the study was to determine if the weights of seals could be determined from the overhead photos. Is there sufficient evidence to conclude that there's linear correlation between the overhead widths of seals from photographs and the weights of seals? Okay, so they've given us these picture widths and weights of seals. So I'm assuming they had some kind of, seals in captivity where they could both, fly over, maybe with a drone or something, take a picture of these seals, and then also see the weight, and what, or be familiar with the weight. Okay, so maybe there's some kind of zoo situation, and they know which seal's which, and they can weigh them and take pictures of them, and we're trying to see if there's a relationship. So if the picture width is wide, it would be a bigger seal, and if it's a bigger seal, it should weigh more. That's the idea. Now, all this x squared, y squared, x, y, all that's intermediate calculations that I've done to show you how to do this by hand. Again, we're going to use StatCrunch, but I've also found the sum of x, the sum of y, the sum of x squared, the sum of y squared. This calculating R is quite involved. Okay, it's not hard, but tedious. So in this case, our R value is 0.948. Okay, so what I said earlier is the closer to 0 R is, the less correlation. The closer to positive or negative 1, the more correlation. So here we're at 948. So 948 is very close to 1. So without looking at it too much, I could, say pretty confidently that this is correlated, right? But there's got to be some cutoff. What if we got, an R value of 0.8 or 0.7 or 0.5 or 0.4? Where does it go from correlated to uncorrelated or vice versa? Okay, that's where this table comes in. We have a new table. And what we need for that table is we need to know what alpha is, and we need to know our sample size. So in our problem, we have the significance level of 0.05, and then we just count how many pictures we have. So we have, width of 7.2, 7.4, so 1, 2, 3, 4, 5, 6. So we have 6 different seals, and our alpha is 0.05. So if we line up 0.05 with an end value of 6, we get this value there. So what that's saying is we need to have an R value that's at least 0.811 to consider this correlated. So it has to be at least 0.811 away from 0. We had 948, I think it was. So that was certainly enough to say there's correlation. So if we had a correlation value of say 0.7, that wouldn't be enough. That would not be considered correlated. It's got to be at least 0.811. And notice that this changes as Rn changes, the restriction changes. Okay, so there's no set number that we have to check every time. It changes based on our sample size and our alpha. So we have to just check that. So that's what I stated here. We have our R value of 948, and that's above our critical value, meaning more extreme, either closer to positive or negative 1. So we reject HO and assume that there's linear correlation. Okay, so as long as our R value is above our critical value and absolute value, then we're going to show that there's linear correlation. Okay. All right, now let me show you how to do this on StatCrunch and see how StatCrunch can help us here. I have those widths and weights in those first couple rows, and we're going to go under Stat, Regression, Simple Linear. Okay, so everything in this chapter, we're going to go to the exact same place. Stat, Regression, Simple Linear. Okay, we select those variables, the width and the weight. And we don't have to change anything else. We just have to throw those two variables in and we hit compute. Now we're going to have a really big output for this. Okay. And it's actually 2 pages. The second page is a graph of those points. And we can see as those, we can see a pattern to those points. As the width of the seal goes up, so does the weight. Okay, which makes sense. The bigger the seal, the more it's going to weigh. Now, what we're looking for here is they gave us our R value. Okay, so all that calculation I did by hand, they've given us that R value there. So one way to see if the linear correlation exists is to see if that's above our critical value. So our critical value from our table was, in this case, 0.811. Okay, so it's above 0.811, so therefore it's linear correlated. We also have another option is to look at the slope row and the p-value. If the p-value is less than alpha, we reject HO, and there's also linear correlation. Either way, that works. Okay, so again, we can compare our critical value, the 811, to our R value. If the R value is more extreme than our critical value, there's linear correlation. Or if the p-value is less than alpha, there's linear correlation. They'll both agree every time. It's just a matter of which one you want to do. Okay. So there is correlation. All right. All right. Now we're going to go into section 10.2, and what 10.2 is basically a regression equation, and we'll figure out why we actually care if something's linear correlated or not. Okay. So here we have this regression equation. Now it looks all fancy, you know, y hat equals b naught plus b1x. Realize that's just a linear equation, the y equals mx plus b that you thought you're done with in college algebra. It's just a linear equation. It's just they're using fancier variables. That's all. Okay. Now, what a regression equation is for is we take one variable, x, and we use that to predict what y is. So in our seal data, what we could do is if we take a picture with x and plug it into this regression equation, that'll predict the weight of the seal. Okay. And that only works if there's linear correlation. All right. So that's why we decide, or why we check to see if there's linear correlation or not, because that tells us if we could use our regression equation or not. Okay. So again, we use one variable to predict the other. Now let's figure out why we would ever want to do this. So say we're a biologist in, say, Oregon, and they're worried about the seals in the ocean not getting enough to eat. You know, maybe the salmon numbers are down. They're worried that the seals aren't getting enough to eat. So they call us, the biologists there, and say, hey, we need the average weight of the seals off the coast. Well, that's pretty hard to find because that ocean is very rough. The coastline is very rugged. Water's very cold. So it's not like you can just go down to the beach and put a scale on the sand and, yell at the seals to line up and, stand on the scale or sit on the scale. That's not going to happen. And, trying to go out in a rough ocean and capture a seal to weigh it is not going to work very well. I doubt they're going to be real helpful in that process. But if we know that two variables are related, meaning linear correlated, what we can do is we can fly a drone up and down the coast, and when these seals are taking their afternoon siesta on the rocks, we fly over with a drone, we take a few pictures, and from the picture width, we can use that to predict the weight. So then we can get an average weight much easier than trying to capture seals and weigh them on the ocean or anything else. Okay, so we can use one variable to predict the other as long as there's linear correlation. Okay, so that is what we have in this case. So the way we find this regression equation, we can find the slope and the y-intercept, with these formulas. We'll have StatCrunch do all that for us. I did do that below, but let's talk about our assumptions here. We have the paired XY data as a random sample, so we have to randomly select our seals. The scatter plot shows the points approximate a straight line. Okay. And outliers are removed known to be errors. That's a little bit beyond what we're doing in this class, the outliers. If there's one seal that's very different from the rest, sometimes we take those out, depending on, how far they are and so forth. That's kind of a little bit beyond what we're trying to do in this class. So let's not worry about that too much. I just wanted to put it in there as, kind of food for thought, I guess. All right. And then this is important. This is where the issues occur in this section or this chapter, and I'll emphasize this a couple times. But if what we're going to try to do is we're going to try to predict some value of y based on some value of x. So in other words, a seal's weight based on some picture width. And we have two cases, and the two cases depend on whether we have linear correlation or not. If there's linear correlation, like we have with the seal's picture width and weight, we use the regression equation. If there's not linear correlation, then we just use the mean of the y values. So the mean weight of all the seals. Can't do anything better than that. So we always have to check to see if there's linear correlation. If there's linear correlation, we use a regression equation. If there's not linear correlation, we just use the mean of the y's. All right, so from those exact same seal data, it says using the same seal data from the above problem, find the best predicted weight of a seal with if the overhead width measured from a photo is 2 centimeters. Can the prediction be correct? What is wrong with the prediction? Predicting the weight in this case. Okay, so what I've done is I've used those same numbers that I've copied over before, and I figured out what the regression equation is. Okay, so here's our regression equation. Okay, where x represents the picture width and y represents the predicted weight. So the idea is if we plug in a particular picture width, then we should get an estimated weight for the seal. Okay? And this only works because there's linear correlation. Now, in this case, they want us to predict for a photo that is 2 centimeters wide. Okay? So what we do is we take that 2 and we plug it in for x. Okay, so that's what I did here. So it's 2 times 40 minus the 156, and I get a predicted weight of negative 76 pounds. Okay, so obviously that's not right because we can't have a negative weight. So let's figure out why this regression equation, after I said how great it is and how well it works, why it didn't do very much at all. It was actually gave us something that's obviously wrong. So if we go back to the data, if we look at these picture widths, the smallest one we have is 7.2 centimeters, and the largest one is 9.8. Okay. Now, what we're trying to do is we're trying to plug in a seal picture width of 2, okay, which is well outside that range. Now, when we build a regression equation, it's made for this range from 7.2 to 9.8. Okay. Outside that range is called extrapolation. And if you go out a little bit, you're probably okay. If we put a seal with a width of 7, you're probably fine. Seal width of 10.1, probably fine. But we're trying to go way outside that range by plugging 2 into it. And the reason why we're getting nonsense out is because we built this model on adult seals, widths of 7.2 to 9.8, and we're trying to put a baby seal into that model. And we can't do that, okay? We have to stay inside that range. So anything in between 7.2 and 9.8, it's going to give us a good prediction. Outside that range, it can give us nonsense. And if we go way outside that range, we do get nonsense. In this case, negative weight. Okay, so we can't go outside that range. Okay. All right, so let me show you how to do that on StatCrunch and how that can help us. We're going to go to the exact same place. Stat, regression, and simple linear. We select that width and the weight, and we hit compute. And we're going to obviously get the same thing out because we did the exact same thing. But in that, they've given us a couple things. Notice this red line. That is the regression line that they found for us. So when we go to predict for something, say we're trying to predict for a picture width of 8 centimeters, basically we go up to this line, say, okay, if it's 8 centimeters, then our weight is going to be, looks like about 165 pounds, give or take. Okay. Notice that it doesn't go all the way down to 2. It's, staying in between, looks like 7 and 10. Now, they've given us the regression equation here. So the same thing I did by hand. They've given us a regression equation. And we've already figured out that there's linear correlation because this is above our critical value and this is below alpha. Either one of those will be sufficient. So we can, use our regression equation and plug whatever value they give to us into that. Okay. All right. Now let me spend a second trying to emphasize this in the homework. Let me see if I can pull that back up. Okay, so we're going to look at these couple problems in 10.2, and I want to emphasize the difference between when we use the regression equation and when we don't. Okay, so in this problem, they give us a whole bunch of stuff. It says, suppose IQ scores were obtained for 20 randomly selected sets of siblings. The 20 pairs of measurements yield mean of the x, mean of the y, an r value, p value, the regression equation, where x represents the IQ score from the older child. Find the best predicted y hat given that the older child has an IQ of 104. Okay, so basically what they're saying is these sets of siblings have they're comparing the IQ scores of these sets of siblings and seeing if we can predict one sibling's IQ from the other. Okay, so assuming they have the same genes, they should have relatively close IQs. That's what they're thinking here. Okay, so we have this regression equation, and we're trying to predict for 104, an IQ of 104. Now, what we have to be careful about is we can always find a regression equation. It's not always useful. We have to figure out if it's useful or not. Okay. One of the ways we can do it is we can look at the p-value. Okay, so we have a p-value of 0, and we have a significance level of 0.05. If the p-value is less than alpha, then there's linear correlation, and the regression equation is good. Okay, so our p-value is 0. That's less than 0.05. So our regression equation is good. We just have to plug in the 104 in for x. So 0.88 times 104 plus 1461 gives us our 106. Okay. Another way of doing it is looking at our R value. Okay, that's pretty close to 1. But if we go to our table, we can figure out, is that high enough to say there's linear correlation or not? So to check that in the table, we have to know, okay, how big is our sample size, which is 20, and what's our alpha? 0.05. So if we go to our table here, I can't quite, let's see if I can. All right, so we go alpha 0.05 is the first column, we'll go down to 20, and our cutoff there is the 0.444, the 0.444. So our R value has to be above 0.444 in order to say there's linear correlation and use the regression equation. So here we would use the regression equation, no problem. Now, if we go to question 2, this one's very similar, and I want to show you the difference here. So it says heights and weights are measured for 100 randomly selected adult males, and the range of heights is 132 to 194, and the weights 40 to 150. Let the predicted variable x be the first variable given. The 100 paired measurements yield a mean of the x is mean of the y's, r value, p value, regression equation. Find the best predicted value of y given the adult male who is 189 centimeters tall. So this is very, very similar. They give us a regression equation, and they want us to predict for a height of 189. Okay, what's the weight if the height's 189? Now the problem here is we have to check to see if there's linear correlation. One of the ways of doing it is comparing the p-value to alpha. If the p-value is less than alpha, then there's linear correlation. In this case, the p-value is not less than alpha. So the regression equation, even though we have it, it's no good. Okay. Another way of doing this is looking at the R value. Okay, our R value is 101 or 0.101. And if we go to our table, we can figure out how far away from 0 we have to be. So in this case, we have a sample size of 100 and alpha 0.05. So if we go to our table, okay, 0.05 is our first column, we go down to 100, it has to be at least 0.196. Okay, so to be linear correlated, it has to be at least 0.196. We're at 0.101. Okay, so we don't have enough to say there's linear correlation. So even though we have this pretty regression equation, is not useful. So when we predict, we do not want to use that. The only thing we can do when there's not linear correlation is just give the mean of the y's for our answer. So that's where this 8146 comes from. Sometimes they calculate that mean for you, and other times you actually have to add up all the y values and divide by however many there are. Okay, so these problems look very, very similar, and all I have to do is just change a couple numbers. You know, if I make this r value instead of 101, I made it 201, then there would be linear correlation, and we would use the regression equation. Okay, or if I made this p-value 0.017, again, we'd have linear correlation. So you don't have to change the numbers by much, and you do the problem completely different. So be careful on that. All right. Any questions on that? I'll hesitate there for a second. All right. So let's look at this problem that back to our fish data that my friends and I collected. And what we're looking at is the lingcods. The lingcod, the bigger fish that you know, have high levels of methylmercury. And one of the things we're asking ourselves is, you know, do all the lingcods have high levels of methylmercury, or does the methylmercury increase as the size of the fish increases? Okay, so so what I want to do is say, you know, is there sufficient evidence to conclude that there's linear correlation between the overall length of lingcod and methylmercury in lingcod? Is there a relationship between the size of the fish and the methylmercury? Now, I have, you know, the summarized data here. I have the length of all the fish that we caught on that survey, the weight of them, and, you know, the methylmercury levels. Now, ideally, I would like to, you know, I think weight would probably be a better predictor of methylmercury than length, you know, because you can have a short, fat one, you know, that means he probably ate more, and if he ate more, he probably has more methylmercury. The problem with these weights is I know how they were collected because I did it. And, you know, we would catch one of these lingcod, and we had this little scale. It was a digital scale, and you'd hook it on the, you know, the fish's jaw, and you'd hold it up. And after like, I don't know, 3 or 4 seconds, the scale would lock into its weight. But the problem is we're trying to do this on the ocean, and it's rough. So, you know, as we're trying to hold this fish up with this scale, you know, we're rocking back and forth. Well, the weight is changing drastically depending on if you're on the upswell or downswell of the wave. So all these weights are wildly inaccurate because, you know, the ocean's moving and you couldn't get a good measurement. So I know these weights are not accurate, so I don't want to use that to predict because it's just they're not good. So the length is a lot easier to do because it doesn't, you know, length doesn't change in a moving boat. So those are pretty accurate. All right, so I have these lengths and weights and methylmercury levels of the lingcod here. So if we want to see if there's linear correlation between these, we would go under our regression and simple linear. We select that length and our methylmercury. And if we hit compute, let's see what we have. Okay. So we have our R value of 0.8 and we'd have to check, see how many, see what our cutoff score is from our table. Or what we can do is just look at the p-value of the slope. Is that less than our alpha of 0.05? Well, as long as that's less than 0.05, that tells us there's linear correlation. Well, our p-value is essentially 0. So not only does that say that there's linear correlation, but strong linear correlation. Okay. All right, so let's go back to our question. I think I have all this, and yeah. So I have all these results. This is the stat crunch results. So we have our methylmercury regression equation. We have our R value. We just talked about the p-value of the slope. And since, here I have all this in red actually. So the first question is there sufficient evidence to conclude there's linear correlation between the overall length of Lingcod and methylmercury? Well, so what we can say is from above, we can see there is linear correlation. There's two ways of doing that. The p-value is less than alpha, or the R value is more extreme than the critical value from our table, which happens to be 0.486. Okay, so either one of those will tell there's linear correlation. If we have linear correlation, then that regression equation is good. So our last little piece here is what is the predicted methylmercury level of a 32-inch Lingcod? So if we catch a good sized Lingcod, what is the methylmercury estimate? So if we plug in 32 in for our length, okay, so we plug in our 32. So we 32 times the 0.1165, and then subtract the 282, negative 2.82, we get an estimate of 0.90 parts per million of methylmercury. Okay, so that's well above what women and children are supposed to eat. That's, the predicted value is twice what the do not consume level is for women and children. So, the bigger Lingcod definitely have more methylmercury, and we learned something. It's just we catch a lot of these Lingcod, and the big ones we no longer want to bring home because it's just loaded with methylmercury. Still delicious, but not good for you. Okay, so we can look at the graph. You can see as the fish gets bigger, so the methylmercury goes up and up and up. So, for instance, if we had a 30-inch Lingcod, that would have a methylmercury level around 0.6. That's supposed to be a straight line. Okay, so the cutoff for methylmercury for women and children is around 0.44. So the cutoff is roughly here. So only the small fish have lower methylmercury than that. Any even medium-sized fish has more methylmercury, and the large fish have way more methylmercury than that. Okay, so it's off the chart. So that's something we learned from this. All right, any questions on that? Okay, now let's look at this goodness of fit. Okay, so this is a multinomial experiment. So we have similar requirements as we had for the binomial. We have fixed number of trials. They have to be independent. Outcomes of the trial must be classified into exactly one of several different categories, and then constant probability. So instead of just having two categories like we had with binomial, we can have a bunch of different categories. These notations aren't going to make any sense right now. I'll come back to those in a second. And we got to randomly select our data. Data consists of frequency counts for each of the different categories, and each category has have an expected frequency at least 5. Okay. Now let's kind of explain what we're trying to do. I think I can do this. Say we are working at a tire shop and we change tires all day, flat tires. And say throughout the week, we are changing tires, and we change 100 tires throughout the week. Okay? Now, what we'd expect is that, so this would be our expected values. What we'd expect from those is that each tire went flat at equal rate. So in other words, we'd have, out of those 100, that 25 of them would be the front left, 25 would be on the front right, and then 25 in each one of the back corners. Okay, that's what we expect to happen. Each tire goes flat at the same rate. Okay? Now, say 1 week we actually kept track of this to see if that was actually true. So we observe what happens. So maybe this front left, we had 40 flats from there. And then the front right, maybe we had 41. And maybe we had 9 in the back left and 10 in the back right. Okay. Now, if we compare these, we can see that what we expected is each tire goes flat at the same rate, but what we actually observed is the front tires go flat more often than the back tires. Okay, whatever, we hit the curve first with the front tires, we run over the nail with the front tires first, whatever it may be. So what we expected and what we observed are different. Now, if we kept track and maybe there's 24 here in the front left and 26 here, and maybe, I don't know, 23 here. What's that left over? 27? 27 here. Then what we observed and what we expected agree. Okay, so this is kind of what we're looking for. We're expecting particular numbers. The top observed is very different than what we expected. The bottom observed is pretty much exactly what we expected. The numbers are very, very close. So that's what we're trying to do, saying, do we have the top case or do we have the bottom case? Do they agree with what we expected or do they disagree with what we expected? Okay. Does that make sense before I delete this? I don't want to write all that over again. Any questions on that? Okay, so keep this in mind. This tire example, we're expecting, 25 in each corner. And, this top case, that's very different from what we expected. And the bottom case is very close to what we expected. And that's kind of what we're doing, saying which case do we have, top case or bottom case. Okay. We have this new test stat. This is called chi-squared. Okay. And what they're doing to calculate that, we're taking the observed and the expected from each one of those. So like we were expecting 25 in each one of the corners, and like the front tire, we observed 48 flat tires in the front. So there's measuring the difference between what we expect and what we observed. So if we compare that first one we observed, then the chi-squared value is going to be very high because they're different. And if we look at the bottom example where the numbers are very close to the same, the chi-squared value is low, meaning that they're what we expect and what we observe are pretty much the same. The degrees of freedom in this is k-1. It's not the number of tires; it's the number of groups. So if we're looking at the flat tire example, we had 4 different groups: the front left, front right, back left, back right. So the degrees of freedom would be 4 minus 1 or 3. We'll come back to this new table here in just a second. All right, so let's see an example of this. So it says an author of the book drilled a hole in a die and filled it with a lead weight, then proceeded to roll it 200 times. Here are the observed frequencies for the outcomes: 1, 2, 3, 4, 5, 6. Okay, and they give the outcomes. He used a 0.05 Sims level test to claim that outcomes are not equally likely. Does it appear that the loaded die behaves differently than a fair die? Okay, so this author is trying to make a die unfair. So the way he wanted to do that is he took a die and he drilled a hole in it and added some weight, and I guess painted it up or whatever he needed to do. Now, obviously he's trying to cheat on some kind of gambling game or something, but he wants to actually make sure that he added enough weight to make sure it's actually, doing what he's wanting it to do, whatever number to come up more frequently. So the first thing we have to do is figure out what would we expect if it was a fair die. So he rolled it 200 times. And if he rolled 200 times, 1/6 of those are going to be ones, assuming it's a fair die. 1/6 of them would be ones. 1/6 of them would be twos, threes, fours, fives, and six. So our expected value is 1/6 of 200, or 33. So we're expecting 33 ones, 33 twos, threes, fours, fives, and six. Just very similar to the tire problem. Each one of them is equally likely. Okay. So that is our HO. So our HO is that every number comes up equally likely, and that is 1/6 of the time. All right. Our H1, they're not equally likely, and that would mean the die is unfair. So HO is saying the die is fair. Okay. And if, oops, I should, okay, it's supposed to say fair. Okay. And this, when it's H1 is not equally likely, that means it's unfair. So it means that the lead weight actually did change the outcomes. Okay. So we assume it's fair unless we can prove otherwise. Step 2 is our alpha, they tell us it's 0.05. And our test stat is just distinguishing, okay, we were expecting 33 ones and we got 27. We're measuring the difference. How far those are apart. Okay. And then the number 2, we had 31 twos. We're expecting 33. We had 42 threes. We're expecting 33. And we calculate all these and add them up and it comes out 5.86. Okay. And we'll have StatCrunch do this for us. Now, to figure out which case we have, is the die fair or unfair? We have to figure out, is this number far enough apart? Okay, are they what we expected and what we observed the same, or are they different? And we're just using this test stat to figure out, is that far enough away or not? Now, the way we have to figure out if it's far enough away or not, is our critical value in step 4. We have our degrees of freedom, which is the number of die minus 1, our number of sides in the die minus 1, so 6 minus 1 or 5, and our alpha of 0.05. Okay, so let me show you where that's coming from. Okay, so we have our alpha 0.05 and our degrees of freedom of 5. We line up that row, that column, and for us to say that die is acting unfair, we have to have a test at least 11,071. Okay, so they have to be a chi-squared value of at least 11.071. Now, what we found was it was 5.8. Okay, so even though he tried to add a lead weight there to make the die unfair, he didn't add enough weight, or did not make it unfair. It actually too close to a fair die to say that it's working. Okay, to show that his die was unfair, it'd have to be at least 11, and we only had 5.8. Okay? And that's what I'm saying in step 5. Since the test stat does not fall in the critical region, fail to reject HO. In other words, the 5 is not above the 11. Okay, so it has to be above the 11 for us to say that the die was unfair. And then we go to step 6, which is our from our table from chapter 8 to figure out our final conclusion. So there is not sufficient evidence to support the claim that the outcomes are not equally likely. Okay, so we're saying that die is still fair. All right, let me show you how StatCrunch can help on this. Okay, so I have a column with the observed frequencies for our die. Okay, so they had 27 ones, 31 twos, so forth. Now we're going to go under stat, and this is called a goodness of fit. So we're just trying to figure out, does it fit what we expect, or does it not fit what we expect? So goodness of fit and chi-square test. So stat, goodness of fit, chi-square. We need to select our observed column. And then expected, we're going to, the default is select a column. We just always select all cells in equal proportion, meaning we want all numbers to come up equally. So whether it's a tire problem, which each corner is 25 flat tires, or it's a die that each one of them comes up 1/6 of the time, or 33 and a third. So if we compute, There's expected, we're expecting 33, we got 27, we're expecting 33, we got 31, so forth. Here's our step 3, the chi-square value. And here's step 4, our p-value. What we did before is we said, okay, is this chi-square value above our critical value of 11,071? And it was not. Okay. Another way of doing that, so 71. Another way of doing that is looking at our p-value. Is that less than our alpha of 0.05? Either one of those. Okay, so is it above 11,071? No, so we fail to reject. And is the 3201 less than 0.05? No, so we again fail to reject. Both of those will give you the same result. So as soon as we say fail to reject, that means our die is acting fair, even though we put a weight in it. Any questions on how that works, or? Okay. All right, and then we have our final section here. So here we're talking about contingency tables. So this is a two-way table. So requirement 1 is randomly selected data represents the frequency counts in a two-way table. So we have two different variables. We're trying to figure out if one affects the other. Okay, so let me give you an example. Maybe on one axis we have Democrats, Republicans, and Independents. Okay, and on the other axis would be their feelings on whether abortion is okay or not. Okay. Well, what we're trying to do, does what political affiliation you're in affect your feelings on abortion? Well, I think that's pretty obvious that that is, very strongly related. So that would be something that would be dependent. Okay. Something that would be independent is maybe uh, male and female and passing a class or not. Okay. Does your sex have anything to do with passing the statistics class or not? Okay. Of course it doesn't. So those would be independent. So that's what we're trying to do. See if the two variables affect one another or not affect. Are they dependent on one another or not? Okay. So I did not mean to click that. Okay. So our HO is that row and column variables are independent, meaning one does not affect the other. So sex and passing the course or not. H1 is that they're dependent, meaning your political affiliation and your feelings on abortion. Are those related? Yes. Okay. So independent or dependent. And the other requirement is that the expected frequency has to be at least 5 in each cell. The degrees of freedom is funky. It's the number of rows -1 times the number of columns -1. And we'll look at that in a second. Our test stat is exactly the same. We're measuring what we observed minus what we expected. We're telling, seeing if they're far apart or close together. Okay. So it's the same test stat as before. It's just whether these two are close or far apart. All right. So let's look at this problem. So it says in a clinical trial of the effectiveness of echinacea for burning coals, the results in the table were below were obtained. Use a 0.05 Singles level to test the claim that getting a cold is independent of treatment group. Okay, so what are the results suggest about the effectiveness of echinacea as a prevention against colds? All right, so we're trying to figure out if echinacea has any effect on whether you get a cold or not. Okay, so we have these three groups: the group that takes a placebo, which is whatever little green pill, and then a group that takes 20% echinacea and 60% echinacea. And we want to compare that to whether they got a cold or not. Does the drug work or does the drug not work? So what we're always going to assume is that the drug does not work, and then see if the expected values, the observed values and expected values are far apart or not. Okay, so let me go down, I'll come back. So our HO is getting a cold and treatment group are independent. That means the drug does not work. And H1 is getting a cold and treatment group are dependent, meaning that the drug does work. It does have effect on whether you get a cold or not. Now, let's look at this expected values. Okay, so this whole table I've calculated. Okay, now the way we do that, let's just look at this first block. So I'm calling that cell 1, 1. We have to take the row total of getting a cold. Okay, so the row total is 178 times the column total of 103 over the grand total of 207. Now StatCrunch is going to do all this for us. And then we do the same thing for, each individual cell. We take the row and column total of that particular row and that column and calculate these. Okay. Now, if we look at this, what we're looking at is saying, okay, we're expecting numbers like this. And these expected numbers are if the drug does not work. So we assume the drug does not work at all. And we have these observed values, and we're trying to see if those are the same or different. So if we look at these two tables, we compare the numbers and say, are they the same or are they different? Well, we're expecting 89, we got 88. We're expecting 14, we got 15. We're expecting 45, we got 48. I mean, these are very, very close. It doesn't look like echinacea works. Now we'll get to the details of that in a second. But let me kind of explain how they do these, because this is how they, test drugs. And these are called double-blind experiments. So what they mean by double-blind is the first part of being blind is the people that are taking the drug can't know which drug they're taking. Okay, let's explain why. So let's say that I think echinacea works and I know I'm taking 60% echinacea. So if I'm in this study and I know I'm taking echinacea every day, a week or two into this study, I start to get the sniffles. I say, well, I'm taking echinacea every day. It can't possibly be a cold. It must be allergies. Okay. So I don't want my bias coming into it. So they can't let me know what drug I'm taking. They make the placebo, the 20%, the 60% all, little green pills that look exactly the same. Okay. So they don't want to let you know which pill you're taking. So that's the first part of the double blind. The second part of the double blind is the doctor, nurse, or whatever that's distinguishing whether you got a cold or not. That doctor or nurse cannot know what drug you're taking either, because you don't want their bias to come into it, or their sneakiness. So in other words, say I'm the one that's making this drug, okay, and I know a doctor, and I say, hey, like, if we can show my drug works, I'm going to make a bazillion dollars. And, I know the doctor, and I, call up the doctor and say, hey, if we can just get this drug, show this drug works, I'm going to have a bazillion dollars. And, I know you like fishing, so I'll buy you the fanciest boat you've ever seen, and you can fish the rest of your life if you want to. All you have to do is just fudge numbers. Can't have that happen either. Okay, so that's where it's a double blind. Nobody, in the actual survey knows what's going on. The only person that does would be an outside independent person that keeps track of each person and whether they got a cold or not. What drug they're taking, if they got a cold or not. Okay. All right, so let's go through this. So again, we assume that getting a cold and treatment group are independent, meaning the drug does not work. And our H1, if we reject HO, is that they're dependent, meaning the drug does work. So we assume it doesn't work unless we can prove otherwise. This test stat is just measuring each individual cell. Like we were expecting 89, we got 88 in the first cell. We were expecting 45, we got 48 in the second, so forth. And we have this test stat of a little over 3. Now we got to figure out our critical value, and that's from our table. So we have our degrees of freedom, number of columns, placebo 20% and 60%. So we have 3 columns minus 1, and number of rows, which is cold, no cold. So that's 2 minus 1. So 3 minus 1 times 2 minus 1, grand total of degrees of freedom of 2. Okay. So we go up our table. We have an alpha 0.05 and degrees of freedom of 2. We have to have at least 5.991 to show that this drug works. So we have our critical value of 5,991. We have to have at least that to show our drug works. Our test stat is only at 3. So we did not have enough evidence to show that that drug works. So we just found out that the drug does not work. And so that's what we come up here. We fail to reject HO. And then we get to our final conclusion. There's not sufficient evidence to warrant the rejection of the claim that getting a cold is independent of the treatment group. The results suggest that echinacea is not effective for colds. Okay, so echinacea, although that sounds great, it's not helpful. So let me show you how to do this on StatCrunch. So I have that table in there, the observed values. So I have the label of cold, no cold, placebo, 20 and 60%. We go under stat, tables, and contingency, and then with summary. Okay, so stat, tables, contingency with summary. So it's a contingency table. They just have it under 2 things. And now all the columns with actual values in there, we have to select all those, placebo, 20 and 60%. They also require the row variables. It doesn't really matter what you select for this, but if we want to be correct, it's label. It doesn't have any effect on the calculations, but I have the cold, no cold under label. And then we hit compute. Okay, so we have, here's our step 3. This is test stat. This is slightly different value than mine. That's because I rounded all my expected values. They did not. So we compare that to our critical value of 5.991. It's not greater, so we fail to reject. Or we can again look at the p-value to see if that's less than alpha. It is not less than alpha. So again, we fail to reject. Okay. So either way is fine on that. All right, so let me stop there. Okay, that's our last lecture for this course. We have our test next week. It'll be set up the same way. We have a practice test on my stat lab. It'll only be chapters 6 through 9. It will not cover this material. This chapter 10, 11 only has a quiz and a homework on it. So you'll sign up for the test through Canvas and Smarter Proctoring. You'll still be allowed a 3x5-inch card of notes, both sides, and you'll still be allowed the tables and formula sheet. So let me pull up that tables and formula sheet so you guys have that. Okay, let's see. So I'll put that in the chat. Okay, so the tables and formula sheet, probably the most useful thing there is if the tables are going to be there, which will be helpful, but also that that final conclusion flow chart to figure out, the wording for our final conclusion is there as well. So that will also be helpful. Next week, I will not cover I won't cover any more new material at all. The rest of the course. Next week and the week after, I'll be around to answer any questions you guys may have on the proctor test, or if you want to, try to improve your homework score and you have to figure out, back in chapter 3 or whatever it may be. I'll be available, both next week and the following. So the next 2 weeks to just be there for help. So no lecture, no new material. I'll just be there. If you have questions, I will, try to help you out, get that grade where you want it to be. Everything for the course has to be done by April 30th. So that's, coming up not too far. It's what, 19 days away, I think it is. What's the 10th? 20 days away, something like that. So it's now it's just finish all this up, and I'll certainly be available for help, to help anybody along. Anybody have any questions or concerns? Okay. If you guys feel comfortable, you can go ahead and drop off. If you need me next week, I'll be available. If not, good luck.
Yeah, this had nothing to do with the lecture that we just had, but I wanted to ask you, is everything on your end